So in the last video we could see this was a very well-behaved function in that it didn't have any place where there were jumps or breaks in this nice smooth surface. So I wonder about the behavior of other functions.
I want to discuss all this behavior.
Well, good. Let's discuss it with some examples. This is a function that's continuous everywhere that the denominator is non-zero. Hence it's continuous except on the line y equals x. Unfortunately, I couldn't get MathCAD to draw this because the line y equals x goes through the origin and is part of every possible grid I could draw. So I needed to cheat a little bit, and I hope I'm still getting a good drawing. But what I did to cheat with my graph here, this is the one I want to look at, but I multiplied numerator and denominator by x minus y. So x minus y times this, x squared minus y squared. X minus y times x minus y is just x minus y, that quantity squared. And now I still had a problem because if x equaled y, my denominator would be 0. But I cheated and I added some little tiny number there, so it isn't 0. And I guess that's kind of sneaky, but that's the way I had to do it. So that's the function I actually used when I drew this graph. But whoa, that's not the graph. Oh, okay. I deleted something I shouldn't have. And so I'm continuing now with the video and saying that you can probably see that along the path y equals x, let me see where that would be. This is the line here, y equals x. So along the path where y equals x, actually this doesn't look too bad, but I think I finagled this thing so badly that this graph is really not illustrative, because when I multiply by x minus y over x minus y, well, I multiplied by something that could be 0 on this path, and of course you're not allowed to multiply numerator and denominator by something that could be 0, so on that path what I'm seeing here is not correct. But if I went on the path where y equals x, then I would have a 0 denominator and not a 0 numerator, so I'd have something that was undefined. So this should be discontinuous, because on this path we get 1 over 0, or something like that, negative 2x over 0. And so even though my picture might not be the best, that's not a continuous function. Okay. So here's another one. Discuss the continuity of the function and evaluate the limit as xy approaches the origin. Again, a little cheating. This time I think I can actually get this graph to draw pretty well. I say f of xy is 1 minus cosine of x squared plus y squared over x squared plus y squared. Again, at the origin we've got a problem, because if x and y are both 0, then we have something divided by 0, and that's not a good thing. Again, I cheated a little bit with a graph here and added something so I wouldn't get 0 in the denominator, but I do get tiny number. And here's what the graph looks like. I don't know what that looks like. It looks like some kind of a bizarre thing. It's wavy up here in this plane, but as it gets close to 0, then it takes off for the nether regions. So 1 minus, maybe we could even refer to that as something like 1 minus infinity of sorts, because see, cosine of 0 is equal to 1, so we got 1 over 0. That's why it is behaving like it does. So certainly we could probably say the limit of this exists and is negative infinity on any path to the origin. So So it looks like it has a discontinuity at 0, 0, that's for sure. And by converting the function to polar coordinates, you can see we'll get this, f of r theta, or r cosine theta, r sine theta, that's f of xy, equals 1 minus cosine r squared over r squared. And as r goes to 0, this is 1 minus 1 over 0. So 1 minus infinity, and so that goes to negative infinity. So therefore, that one's discontinuous at the origin, at the point 0, 0. You can kind of see, there it is centered there. You can see the hole in it. Keeps on going through that hole, I guess, but it's continuous everywhere else, like you would expect sine or cosine to be. So, the concept of continuity can be applied to functions of 3 or more variables, but I can't draw it anymore then, right? I'm having a hard enough time. But you can't see the drawings to show the jumpy spots. We can still see with algebra where there will exist trouble spots. Okay, the next example should illustrate this, and that'll be in the next video.